Now we already just now before we go for a break, we already help you guys to prove V2 equal to half Umax, which is if you have a parabolic shape of a velocity profile like this, you can convert or equivalent this kind of a profile to Umax in the Umax terms. You can use average velocity to represent this profile. So in the exam, if you're being instructed to, if you're given a parabolic profile like this, and then you are asked to use average velocity to in your analysis, then straight away you use this information. Straight away you use average velocity to calculate the Umax. Okay. Now, how we know the value of Umax? How we know? You check the diagram or in the statement. For example, in this example, you're given U1 equal to U. For example, if in the question, you're given, I go back to the statement. So in the question, if this value is given, velocity is in the section 1, the velocity, the entry velocity, let's say, is 10 meter per second, let's say. So here, the velocity go in is 10 meter per second. So maximum velocity here, Umax at this axis here, along this line, will be equal to Umax will be equal to 10 meter per second, for example. So your average velocity at section 2, when you use V2, you can straight away write Umax divided by 2 equal to 5 meter per second. Okay, so this one won't be given. This kind of analysis equation won't be given in the exam. So you have to understand when you do conversion. When you do conversion, so if you use average velocity section 2, where the velocity profile is asymmetric and parabolic, with zero velocity at pipe wall and maximum value Umax at the center line. When you see this kind of statement, straight away you can use this this equation. Average velocity equal to Umax divided by 2. Okay. All right. Let's look at the next application of what we learned so far. We're still at continuity of mass, conservation of mass, continuity equation. Yeah, so this is how we apply it. The rest is just mathematics. Okay, now let's look at your tutorial chapter 2, question 7. This is application in the construction environment. So, and of course, the picture I extract from the website, and the statement was modified a bit from the example. Okay, now the setting is like this. So construction worker in the trench or in the channel like this. So they dig some channel to replace some pipe or electrical wire, right? So below, install a new water line. So in this case, the install water line. So maybe when you go out there, you work in a civil construction, civil consultation firm, where they employ you as a M&E, mechanical and electrical engineer or mechanical engineer in their company, and work on the construction. need to do some calculation. So you are given the size of the channel here or trench, given a certain size, 3 meter, 1.5 meter, 2.5 meter. Okay. So as a result of being near an intersection, carbon dioxide from the vehicle exhaust, if you turn on the vehicle still running all the time, it will drop from, for example, in this photo, the CO2 will drop into this channel, and then there's a worker there. Now, because this CO2 have a greater density than air, it will settle to the bottom, means it will drop to the bottom, and displace the air in the worker need to breathe. So it will bring it a bit danger to the worker here. So when you go to work, there's a health and safety regulation that need to follow, or SOP need to follow. So if you're not careful, the company will need to pay for the fine and all this. Okay, that assume that there is negligible mixing between air and carbon dioxide. Means there is no mixing. Assume there's no mixing. So what we need to do in this scenario, so there are two tasks we need to solve here. Estimate the time rate of change of the depth of the CO2 in the trench, dH over dt, in the unit of meter per minute in this question. So yeah, so if in the test, this one you need to put in the, maybe you instructed more detail, maybe meter in second, right? So in this case, it's meter per minute. Calculate the time. The second task is calculate the time where your H equal to 1.7. So the total depth is 2.5. Means from here, from the wheel here to the bottom here is 2.5. He asks you to calculate when at the time where at a H 1.7 meter, it would take for the level of carbon dioxide reach 1.7 meter. Means the CO2 from the engine will drop into this channel, and then because of the density of the CO2, it will flooded this channel with CO2 and then keep rising until 1.7 meter. Okay, maybe I'll visualize a bit. So CO2 from the engine will drop, and then the CO2 level will rise up until 1.7 meter. So the question asks you what is the how long it will take to reach 1.7 meter. Yeah, you need to do calculation like this. Okay. The first section is to ask you to find the mathematic model, mathematic equation where the change of height, where the carbon dioxide will accumulate, dH dt here. It asks you, the first section is here, asks you to calculate the mathematic model, and then the second one is you apply what you develop here into the question so that you can find your T. So this basically the application of what we learned so far. And again, because this is a channel with a fixed volume, finite, we are still in the finite control volume. So once every time we have a control volume, we can use continuity equation. All right. So, right, all these are the keyword that I just mentioned. All right, now be careful on the rate again. Be careful on the rate again. This one is 3 meter cube per minute, and the question asks you to answer in the meter per minute. So you can save time without converting into second. So if this one in minute, but the answer asks you to convert into meter per second, then you need to be careful on the unit. Okay, let's look at how we establish the dH over dt for this case. The first thing, draft out the control volume that is given. So I think there's a space in your tutorial there. So you can draft out the for this case. in a space or in your notebook, draft out this diagram. All right. So if you read the question, the trench is 3 meters long, and then 1.5 wide. This is wide, or this is L. This is W, and the height 2.5. Can you assume there's a worker here? All right, and normal Asian people is about 170 to 180 cm height, or put in 1.7 to 1.8 meter. So when you go to work, have some common sense and awareness on the application. Right? So I'll give you some time to draft out the diagram before I move on. All right, and then because we are in the finite control volumes chapter, FCV, so remember to mark your control volume. All right. Now in the final exam, if you're given a statement like this and then you draw out the diagram, you'll be given some marks, 1 to 2 marks for the diagram. Just as an effort to start to solve the question. Sometimes this one not guarantee, but there's a room for marks here. So if you draft out something, you'll be given 1 to 2 marks. Okay, of course, with the control volume, all this with the control volume, the marks, and then CO2 flow from above go into the system. Okay, I'll continue. So if I move too fast, just stop me. If you cannot follow, just stop me. Or you need more time to draw or draft something, just let me know. Okay. Now call out the continuity equation. Del over del T, integration of your control volume, rho dV. Again, V dash means volume. V dash, dV dash means volume, because the first term here is control volume, so it's volume. Second one, control surface. Surface always deal with the area, so dA. Rho V dot N hat dA. Right, so you just memorize. One is about volume, one is about surface in the continuity equation. And don't write d over dt, integrate cv rho dv. This one is wrong. If you write d over dt in here, your continuity equation is wrong. It's del, del, not d. So be careful on the handwriting also. Just make some notes. For continuity equation, the first term is del, partial differential, not the differential. Okay, take note on this one. Okay, now we assume again, we simplify the question. We assume it's stable. Okay, so just a note here. So these two terms consist of air and CO2. Air and CO2. Two medium here, air and CO2, because at the last row of the statement, assume that there's no mixing between air and CO2. There's no mixing between these two. Of course, in the real case, there will be the mixing happening. Yeah. Okay. Now The next step is just you expand the continuity equation. On the left hand side for your control volume, you have air and CO2. So del over del T integrate for air plus del over del T integrate for CO2. This is for the control volume. Now, why we cannot cancel out although the flow is steady? Because the volume is changing. The volume of air and CO2 is changing. So that's why we cannot cancel out, become zero. Again, I repeat. So why we cannot cancel out this one become zero, although the flow is flowing very steady? Because in this case, because we assume there's no mixing between air and CO2, the volume for air and CO2 changing with time. Yeah. All right. Then for the m dot component, the control surface component, we have negative m dot CO2. Why negative? Because CO2 go into the control surface. In means negative. And the air was adding. All right, it was adding, so it's positive. Because the air is flooding out from the control volume, right? CO2 keep filling, the air, some air was pushed out from the control volume because no mixing between these two. So you assume this one like a sand, behave like a sand, and one in and one out. Okay. So be careful on the sign again for chapter 2 on the direction of the flow. When they pass through the control surface, be careful on that one. Yeah. Okay. Now the next one, we will pull the air in one term, one side. All right. We pull one, because we have a mixture of air and CO2. We pull the air into one component, one side, CO2 into one side. So for the CV plus the CS for the air, we get one relationship like this. Right? Then in here, we also need to know that air must be conserved. And CO2 side also must be conserved. So both for air and CO2 must be conserved. Okay, we look at CO2 first because we have information on the CO2. So we focus on CO2 because on the air we don't have much information. But CO2, because our CO2 will enter into the channel with the rate of 3 meter cube per minute. So we have something information about our CO2. So we start with the CO2 component. So you pull out the CO2 component on a CV and CS. So del over del T integrate CO2 rho dV. Again, this is the volume minus because it's going to the control surface. M dot CO2 equals 0. Again, y equal to 0 because we use the continuity equation. So when you integrate dt. So velocity, volume. How you get volume? You get h times, okay, this is your h, this is your length, this is your width. Volume equal to height times length times width. So you put into the equation. So integrate rho dv, we have dh L W. Because L and W do not change here, the height is changing, so we can put dh here. Okay, then you pull all this together, rearrange, you get this one. We have a dt here, you put inside there, you will get del h over del t. Yeah, also we need to change our mathematic sign here. Although just now I mentioned it is a dh, but because our equation is in a differentiation, means very small changes, so we can also modify our relationship into del h here. Del h L W, yeah, is our TV component. You rearrange, then you get this relationship. So del density CO2 del H over del T, 3 times 1.5 meter equal to M2. So this one, we just move what you can see on the left hand side. We just move this one to here. And this one was given in the equation, in the statement, in the statement. All right. Okay. The rest, okay, you expand the m dot. Expand the m dot. All right. Expand the m dot. M dot again. I repeat this one again. Yeah, again.
So,
Yes.
in that what they call the V, the volume.
Volume. Yeah.
We have to times the with 3, right? The 3 times 1.5 times 2.5, right?
Yes, but we in here we need to why we do not substitute the 2.5 here? Because we need to find the relationship of del H over del T. We need to
Oh,
find this relationship.
okay.
That's why we only times the area, the floor area.
Okay,
3 times
understood.
1.5. Yeah. Okay. Yeah. Okay. Now, and then you expand m dot. M dot equal to rho AV just now. This is how I memorize. Or rho Q. It depends on the information you have in the statement or in the question. So in this case, we are given a Q. So we just use a rho Q here. So expand this one into rho Q. And then simplify the equation. Just cancel the density of the CO2. And then you move around, rearrange the equation, pull the 4.5 from left to right, and you're given the QCO2 with its 3 meter per minute divided by 4.5. You press your calculator, you get 0.667 meter over minute. Again, for this module, maximum is 3 decimal place, minimum 2, unless you are given further instruction to give maybe 1 or no decimal place. All right, so we solve for the first section. We already get the relationship, the change of flooding rate, del H, means our CO2 flood the volume at the rate of 0.667 meter per minute, means it will change. And this relationship was developed from the continuity equation, where we break into 2 individual medium. One is for the air, one is for the CO2. And this one was focused on the CO2. 0.667 meter per minute, this one referring to CO2 rate of change of depth. Okay. Now, what happened to the, if the question changed to just give you a bonus mark, just ask you the rate, the change of depth of air. So it will be same, but it will be negative, okay? Because the air is decreasing. The height of the air is decreasing. Okay, we move to the B. Since you already have dH over del H over del T for CO2, so when you move forward to section B to find the time where it reached 1.7, 1.7 is the height of the workers, like I mentioned just now. Typical height for Asian adults. So you know that del H over del T equal to 0.667. So to reach 1.7, you just do a simple calculation. You 1.7 divided by the rate, you will get the time. So because both is in the minute, so you just do the simple calculation. T equal to, you take the height that we want to look for, 1.7 divided by the rate, 0.667 meter per minute. You get 2.55 minutes or 2 minutes 33 seconds to reach this height. Meaning, if we assume there's no mixture of CO2 and air, within 2.5 minutes, the workers will be start flooded with CO2, and then it will show some symptom of poison, air poisoning, or air poisoning symptom, CO2, and then yeah, you put your worker in the risk. Okay. So this is how we solve for the A and B. Section B, this one is just can say as a bonus question. You just apply what you developed just now. Yeah. And then A section is just application of continuity equation. It just make you confused a bit with the air and CO2. Because the previous example, we only deal with one medium, with its air all the time, or water. But in this case, there's a mixture of two medium. And yeah, and our volume here is changing. So we cannot, control volume component, we cannot equal to 0 because it's keep changing. All right. Okay, we have done for question 7. Any question before we move to the next concept? And question 7, I will always have a marking there. So question 7 is still under conservation of mass. However, it deals with unsteady flow. Although in the question it do not mention anything, but this is under category unsteady flow for question 7, Q7. Question 7. And then the previous one is the conservation of mass. It tests you on the non-uniform velocity profile. Still conservation of, this one is for the question number 6. Is mentioned, just highlight the non-uniform velocity profile. Okay, then the earlier one. The earlier one is between two floats, but there's no change of volume here. Two floats, everything fixed, no moving parts and all this. So fixed, then you can use the cancellation of the steady flow. Okay. Right. We move to a new concept now. We have done with the continuity equation for fixed control volume. Now we start look at fixed non-deforming control volume, which is your question 8 there. Question 8 there in your tutorial. So you will see the same diagram. What is changing here? You can see the flow is from the top to bottom, entering from section 1, pass through section 2. So you can see there's a parabolic shape of velocity here in section 1 and section 2 also. What changing here is the volume. The changing of your volume from in and out. Two of these have the same different volume here. Or you can say volume consists of area. So the change of area, you will change your equation, the content of your equation. Right, so what equation you use for this kind of case, where there's a change of volume from one section to another volume, or there's a change of cross-section area to another section. So how we develop the equation. So again, call out the continuity equation again. So continuity equation consists of a control volume and control surface equals 0. Del T integrate density times volume plus integrate of your control surface rho v times the n vector dA. This is the m dot component. M dot equal to rho AV or rho Q. So this one, if the flow is steady, there's no moving parts, there's no change of volume, then this component equals 0. Okay, we start with the continuity equation. So when the flow is steady, this is 0. And yeah, this is also 0. So this component is 0 when the flow is steady. And the mathematic model for the control surface here is m dot. So what is out must be equal to what is in. And why there's a negative in front of the in here? Because of the n component here. Because the flow into the control surface will use negative rather than positive. Positive means it flow out already. Okay. Positive means flow out. Huh? Positive means flow out. Negative means flow in. Okay, we'll deal with the concept first. Huh? So the flow steady, both of these equal 0. But for the control surface component, this is the m dot. I need to recall that m dot have in and out. So what is in? When it's in is negative sign, out is positive sign. So when the flow is steady and incompressible, which is deal with the density rho. So your equation m dot will be simplified into Q term, because m dot will be equal to rho AV. I like rho AV here, or rho Q. So when your flow is steady and incompressible, means deal with the rho, all the rho is same, so we can cancel out. You'll get Q in this equation. So Q out minus Q in equals 0. Why negative in front of the in? Because of the direction. The flow in, you get negative. Okay. Now, okay. Maybe I'll slow down a bit. Let you write some notes in the any space that you can find there. So we deal with steady. And the first one you can write maybe steady and compressible. All right. The second one, if you have the word steady and incompressible, meaning you can take out the density, you factor out the density, then you only focus on the volume flow rate. Q is the volume flow rate. Your area times the float velocity, you get volume flow rate. Okay. The next one, we deal with another two scenario. So when the flow is uniform or non-uniform. So when the flow is uniform, we will use this equation, m dot equal to rho AV, because it's uniform throughout the section. So if the velocity is non-uniform, then we will use the v hat here. The differences is between v and v hat. V hat is average velocity. And we already show when you have a parabolic shape, you recall the v hat equal to v max divided by 2 for parabolic, for parabolic only. Okay, so we have deal with two cases. One is steady, normal one, without mentioning any compressibility. You use m dot like normal. If you see in the statement, you see steady and incompressible, you can still write out the m dot equation. However, at the end, you still cancel out the density. At the end, you focus on the Q, which is volume flow rate. Q out minus Q in. Again, be careful on the direction of the flow. When it's in, it's negative. It's out, it's positive. Okay, and then the second keyword that you most of the time you'll see in the question is either uniform or non-uniform, or from the diagram itself. Uniform means you will see a square box like that, and then you'll see arrow in the same magnitude. You see like that. So if you're non-uniform, you will see like that, parabolic, or just now a non-parabolic, we did a straight and then like that. You'll see this is non-parabolic. Okay, in the slide this morning, you see the difference between these two, and we already cover what happened if you're parabolic. You can use u max divided by 2 to convert this one into this one. Okay. Right. So let's say we only have a steady flow and only one stream of the float, means only one input, one stream and one input, or one opening. We'll use m dot equal to rho AV and average. So when you see average, means you see a parabolic shape here. It's a non-uniform space here. So when you deal with parabolic, then you use average sign in your answer. So because of the continuity equation, m dot here in section 1 will be equal to m dot here at section 2. Whatever the mass will come in here will continue in section 2. What will change is because of the volume or cross-section area, your area will change, density will also change. Velocity also will change. So 6 parameter we're looking at here. Parameter section 1, we have 3. parameter, section 2, we have another 3. So total, we have 6 unknown here. Okay, 6 unknown. So for incompressible, again, this you can cancel out if it is a compressible case. If it's compressible case, take out the density and then simplify into Q form. We have A1 times the average velocity again. I have to mention it. It is average velocity because of the non-uniform profile. Yeah. So at this moment, we're still dealing with continuity equation, and we deal with a certain concept. What happens when it's steady? What happens when it's non-steady? What happens when it's uniform? What happens when it's non-uniform? What happens when it's incompressible? Okay, we still look at a mathematic model, and then we will use we will go for application. Now, just now it's fixed. Control volume. What happened? We what happens if we look at moving control volume, moving non-deforming control volume? With this one is question 9 in your tutorial question. We already completed question 8 just now. So these are the equation that when we deal with fixed non-deforming CV control volume, we'll use all these equations that you see on the screen just now. So these are the concepts that you should always remind yourself when you see all these keywords in the question. So the next one, we look at moving non-deforming control volume. So this one will be, I'll give you 2 examples here. So what I mean by moving non-deforming control volume? So one of it is on the screen here. You will see the turbine, the aircraft engine. It will suck in air from one inlet and then push the air in another outlet. Okay. And another one is the ship here is moving across the sea surface. Right. So more easier to grab the idea is looking at the aircraft jet engine. So you see there's a different shape of the jet engine, different cross-section area. When the air moved from the front to the back, the area was changed. For example, in this case, I highlight the fan component. The area is a little bit larger. And then we go into compression chamber. From this area, your A change to a smaller A, and then combustion, change the A again into afterburner or second compression. Then you will change area again. So we are looking in this kind of case now, moving non-controlling volume. So when we have this kind of scenario, how we deal with it? So we will look at vector form. So when you deal with a velocity, we know that velocity is a vector with magnitude. So right somewhere in the space there, you have 3 components you need to focus on. Okay. V, this one, I explained the V first. The V is a normal velocity that you see in daily life or in the normal question. V is an absolute velocity. So let's say you stand here. Let's say this is you. You see a particle or something fly in this direction. So this V component is what you see with from your eye. V from a stationary observer at a fixed coordinate. So you stand here, you see the V. This is the normal velocity that you see. Then you break these two. V you break into two components. One is called denoted by W capital and V control volume. V sub CV. So let's look at what is W. W by definition is the fluid velocity seen by an observer moving with the control volume. So it's a relative velocity. Relative velocity. Later we look at example, then you will have more idea about this one. So at here we look at the definition first. So W is relative velocity. This one with the moving with control volume. Okay, moving with the control volume. And then the velocity VCV is the control volume velocity. This one is seen from a fixed coordinate system. It's a bit different from the V. V is from the observer. VCV is from a fixed coordinate system or reference point, a different reference point. Okay, write somewhere these three terms here. V is absolute velocity. W is relative velocity. And the distance or the difference between W and V, we call it control volume velocity. So in the vector form, you start with W, continue with VCV, then your V is a resultant of your vector. All right. So this is a vector diagram. It's a vector diagram and it's fixed for moving and non-deforming control volume. This shape fixed already. It means your W, you always start with the W, continue with your CV, your VCV can change either this way or this way, but you always after the W. And the starting point of W connect to the end point of VCV will become the resultant, or we call it V, absolute velocity. Okay, so this is a vector format. So vector concept. So we have to recall it if you forget. Right, let's look at application already. So how we apply this one in the Reynolds transport theorem. So we relate these three as in the equation. So V equal, this is still, you can find some space in question 9. V equal to W plus VCV. This is what the vector form will give you. Meaning the absolute velocity is a combination of your W plus VCV. Okay. Now, this is question 10 already. So when we consider a moving non-deforming CV, we pull out the Reynolds transport theorem that derived for the continuity equation earlier. This is from our first slide, chapter 2. We mentioned the mass system, the change of mass system or m dot system. You can write m dot for this whole thing, right? But m dot means d, right in the differentiation format, dm system means mass of the system divided by dt equal again control volume and control surface. So del over del t integrate with your rho d volume. You've seen this one many times just now. And the control surface component also. Just now we have rho v. We have rho v dot n hat dA just now. For moving non-deforming control volume, we will not use V, but we'll use W component instead. Take note now. For moving non-deforming control volume, for control surface component, the velocity here, we will use the W, which is the relative velocity. Okay, copy this one down for question 10. We will start deriving the equation for application moving non-deforming control volume case. So we start with a dm system over dt equal to del over del t control volume component plus del over control surface component. Remember to change your velocity vector, focus on the relative vector, which is W in this. I highlight with the red color. And then what is the relationship W in this vector diagram? Which is V equal to W plus VCV. So previously we only focused on V, previous slides. Now we have two more terms to focus on, which is W and VCV. Okay, let's look at how we apply this one. Now, for conservation of mass equation, just now you have the Reynolds transport theorem. So for conservation of mass, how this Reynolds theorem will become. Again, conservation of mass, the whole total changes in the control volume and control surface will be equal to 0, which means the whole Reynolds number, Reynolds transport theorem will be 0 to define for conservation of mass. All right. So for question number 10, when you want to define a system, you start with the Reynolds transport theorem, which is you write out the equation. Again, be careful on the velocity component here. We no longer look at the V, we look at W now. We focus on relative velocity now for moving control volume. Again, moving and non-deforming. So moving control volume, meaning your control volume now is moving already. For the previous section, our control volume do not move. Only our fluid moving. Now, we are focused on the moving control volume. We are focused on W vector instead. Okay, let's look at one example and then we call it a day. So look at your tutorial question number 11, which is application of moving control volume. Again, every time you think out of moving control volume, there are two examples just now. One is the boat, one is the aircraft engine. So let's look at aircraft engine. All right. Question 11, if you read the statement. So airplane move forward with a speed, certain speed, and this one is given in kilometer per hour. So be careful on the unit SI again. The frontal intake area, with this highlight in the diagram there, given so and so. Intake area given, your A is given 0.8 meter square. Entering air density is given. So density now is given already. Previously, we do not see this number, but now is given because density change when you have a moving control volume. So a stationary observer determines that relative to the Earth, relative, you start to see this special keyword already. You start to see this keyword already, relative. Relative. The jet engine exhaust gas move away from the engine with the speed of this one. So there are many quantitative quantity here. The quantitative parameter here given already. Engine exhaust area, which is A, was given 0.5 meter square, and exhaust gas density is given also. So you have speed here, you have density here, you have area here. Okay. Now we are apply what we learned from the question 8 diagram. There's a change of area, there's a change of density, there's a change of average velocity also. Now this application in question 11, it asks you to find the mass flow rate of the fuel into the engine in a unit of kilogram per hour. Okay. So how do we solve this one? So all these parameter I mentioned just now, all the important parameter, you need to keep an eye on them. And then I want you to draft out the diagram somewhere in your notes there. So in the exam, you need to draft something. All right, you need to draft out something. Visualization is important as an engineer. When you want to solve something, visualize it with a diagram. In this case, you draw out the control volume. Right, I give you some time to draw it out. So you draw a cylinder with a different cross section. You don't draw a cylinder. If you in the exam, if you draw a cylinder like this, meaning you don't understand the question. You can draw something like that. It's all right. This one is better than this one. Then you can mark section 1, section 2, and then there's a few inlet here. All right, section 1, section 2. Put in all the parameter given. You have forward speed V1, V plane here. Right, V1, V2, A1. This A is given. Yeah, A is given. So A2 is given. So I'm going to explain a little bit on the diagram. I'll let you one more minute to draft out the diagram as I show on the screen. Again, in exam, you need to explain something with the diagram. Okay. In your lab report also, after you get the data, you need to draft out to explain your argument, your explanation. You need to draft out something, a diagram, just to explain what do you mean. Okay, I'm going to explain the W because in the moving control volume, we focus on the velocity vector, which is denoted as W, the relative velocity vector. Okay, I think I don't need to explain about the velocity in and out already. Okay. The V here, you see the arrow. V plane is moving out. V plane equal to 971. V2 is the exhaust velocity, 1050. And then there's a fuel go inside there. This is what we're going to find. The question asks us to find what is this. And then remember on the control volume, make sure you draw out the control volume. And then mark the point, your boundary condition 1 and 2. Where is section 1, where is section 2? Now I'm going to explain about W1 and W2. Now W1 is a relative velocity from a fixed position. All right. So you're going to see the flow, we're going to suck into the engine front area. So the direction of the fluid, you focus on the air itself. You focus on the air itself rather than the plane. You focus on the air. The air going to suck in. We're going to pull inside the engine with the velocity 971. So this one will become the arrow direction will going in. Imagine you are the air itself. Where do you go when you face the engine? So you're going to suck in. So you're going in. So draw the arrow going in. W1, you write W1 equal to 971 km per hour. And then we're going to look at W2, section 2. So imagine you are the air particles. You go into the engine and then you're going to push. You're going to push out from the exhaust with the velocity 1050. Now remember, you're going in with the inertial velocity 971, and then you further push out from the engine with 1050. So your W, your relative velocity will be the 1050 plus 971. Your W2 will get 2021. Okay, I always use the word relative. In this case, relative velocity denoted by W. Relative means you refer to a certain coordinate or certain point. Okay. So this is how we calculate the W, or how we derive, how we determine the relative velocity of W. Okay. V plane is just a statement, sometimes to confuse you. But again, focus on the velocity. Imagine yourself, we are focusing on the gas. Imagine yourself is a air, and you go into the engine. What happened? Okay. No question. This is just a refresh. What is your W? All right, I'll pull the diagram to one side on the slide. We're going to start solving this question with the continuity equation. So, pull out the continuity equation. Consists of, again, CV and CS, control volume and control surface. I think this one is more than 100 times I mentioned this one for this lecture. All right. So CV plus CS. Again, velocity vector, velocity here we use W for moving control volume. If you write V in the exam, mean you're referring to fixed control volume. You're referring to FCV case. Okay, be careful on the how you your equation in your answer. Huh? Be careful. Right. So this one already, okay. So again, if you look here, there's if you control volume here, your continuity equation, your mass in and out, your in a bigger picture here, your mass doesn't change much. So it's a steady flow. So this one will equal to 0. The control volume component will be 0 because it's a steady. Okay. Then we only have the control surface component with the relative W here. So this equation, come to this equation. Now I need to put it a bit slow here. So again, this component actually is a m dot or rho AV or rho Q. I'm going to repeat this one many times. All right. So m dot equal to rho AV or rho Q. So again, we're dealing with the direction. If you see n hat here is a direction. So what I mean by direction? It means it go into control surface. So if go in past the control surface, it is negative. Again, this is a control surface. If the fluid come out, is a positive. Okay. So here we have fill in. We have front in, front out. So means we have section 1, section 2, and then one of the fuel inject here. The fuel inject into the passing the control surface here, pass through. So the first one, why we use negative? Because it's pass in to the boundary condition, into the control surface here, negative, because it's in. Why negative at section 1? Also because it's going in to the control surface here. Why this one positive? Because it's come out. And again, we do no longer use V here, we use W. Okay, this is just a note here, just to remind you what is m dot. Here we use W1, W2 because this is the moving control surface. Okay, let me clear the pointer here. So you rearrange because you want to find the mass flow rate, m dot in, want to find the how many fuel was pumped into the engine. So we move this one become positive. We move this one from the left to the right become positive. And then we rearrange because we like positive first. So the section 2 component minus section 1 component. Again, minus is because of the direction. Okay, it's because of the direction of your n hat. All right. Now we need to find what is W now. At this moment, we are still repeating what we learned so far, the continuity equation so far. Now only we want to learn one more new thing is how to find the relative W, relative speed here. So there's a side note here. So we know that V2 equal to W plus V, right? V equal to W plus V VC, right? Just now. In the velocity vector just now.
Yeah, control volume.
Yes. In the question 9, you see the volume, the vector diagram. So V equal to W plus VCV. So here our VCV is our velocity of our plane. This is how we apply the theory side. All right. Okay. Now, however, in this case, we focus on the W because we want to find what is W. Right. So W, you move your equation. W equal to W equal to V minus V plane. Of course, this one I focus on section 2. So W2 equal to V2 minus V plane. So you put in the value. V2 in this case is 1050. V plane here is negative. Why negative? Because the direction. Huh? Okay. Now, why? Because let me draw the reference axis here. You have y and x. All the direction to x is positive. All the direction to y is positive. So why this one is negative here? Why I put a negative there? Because of this factor, this direction. Because the velocity of the plane is opposite the x-axis, or is you can say is opposite direction of your W. Right, but you memorize that one as y and x-axis is more simpler. All right, so this is the mistake that most students will fall into. Be careful. You will miss out the negative when it comes to exam. Okay, now make notes. Highlight this one.
But that is output or input. If output means it's positive, right?
No, okay. You don't confuse with the vector. This side is on vector. This equation, negative positive, is on the control surface. This one focus on the control surface. You don't confuse with these two. Control surface, when you have something go into the control surface, in means negative. I think this one you know. Out the control surface, this is positive. This one is different. On the left hand side is more on the vector. It is a different different things with what you see on the right hand side here. Do I explain your question?
Yes, sir.
Can
Yeah, clear.
yeah, clear. All right. Right. Stop me if you're not able to understand. Make me explain until you understand what I'm talking about. All right. So just be careful on this one because this one you're dealing with a vector, and this one negative because of the direction. We're dealing with the vector direction rather than the control focus, rather than a control surface here. We're dealing with vector now. All right. So again, focus on the reference axis, x and y. So whatever go to the right is positive. So again, you see the velocity plane is going to the left hand side, so it's negative. Then you put into mathematic calculation, negative become positive. This one is automatic happen when you do the calculation. Only mistake, most of the student will forget the direction of the vector, original velocity in the setting. So be careful on the conversion from second line to third line here. Because when during exam you panic already and then you focus many things. You will forget many things. Right? Just make a note when you come to exam. When you do revision also. So W2 again is a relative. You get 2021. Like what you see on the diagram here. Of course, in exam, you won't see the W1 component here. Right, you need to draw it up, this diagram. So have a clear picture what is V, what is W, what is VC, CV, VCV. So have to differentiate between these three vector. Okay. Now we have all the value inside for this equation already. We have row 2, A2, W2, row 1, A1, W1. Substitute value there, you get 9100 kilogram per hour. Area, you should know lah, area of the circle. It was given, or in this case is give you a more easier direct instruction. In the exam, we will give you diameter or radius. In this, because this is a tutorial question, we straight away pass through the area calculation. In the exam, you need to calculate the area. Okay, so this is the answer for question 11. This is how we apply the velocity vector, how we apply for moving non-deforming control volume, how we apply the question 9, question 10, and then in question 11. This is how we apply. Okay, question 12, we will continue this Friday. Same concept also. We will walk you through how you apply this vector this equation. Okay, how you apply, where's the velocity? How you apply how you apply this one? How you apply this equation? V equal to W times VCV. You see a little bit example in question 11 just now. VCV just now is your V plane. And then our Reynolds transport theorem. We have a moving non-deforming control volume. You need to change your vector. You focus on the relative vector rather than the absolute velocity. So this is the difference between non-moving and moving control volume. Okay, any question before we end our lesson for today? Anything that you're not clear, any slide or you miss out just now? No? Okay, let me end this recording. Let me see something somewhere. Okay. Let me end.